So, good afternoon, and welcome to the third of three videos on Chapter 6. All right, and this is all about z-scores. We'll start today's video, or this video, with uh, using z-scores to describe sample means. All right, so again, remember what the difference between a sample and a population, but we'll start with the sample idea. I know a z-score, as we said earlier, is simply a method of describing a set of data that is normally distributed, but it kind of standardizes the whole thing because it's based on the standard deviation. Remember that a z-score essentially ranges between -3 and 3, all right? Because there are three standard deviations above the mean and below the mean. So that's a grand total of 6. The mean value is 0, and for every standard deviation you move up or down the distribution, you increase or decrease the z-score by 1. So what exactly is a sampling distribution of means? By definition, it is the frequency distribution of all possible sample means that occur when an infinite number of samples of the same size, n, are randomly selected from one raw score population. All right. Now that's a mouthful. What does that mean? It means that if, let's say, you have a population of 1,000, okay, and rather than wanting to measure every single element in that population, you choose to measure 50 at a time, okay? And so what a sampling distribution means is that you take 50 and you use that calculation. And then you choose another 50 randomly, not the same 50, but another 50 randomly, and then another 50, and another 50, and another 50. And you do this an infinite number of times, all right? Now, technically, there's not really an infinite number because if there's a population size of 1,000, there are only so many combinations of 50 that you can come up with. But it's a lot of combinations, all right? And so when you do this, and then you create a frequency distribution of all of the means that you calculate, that's the sampling distribution of means. And essentially, what it is a more accurate method of determining the actual mean of a population from a sample. All right, if you only use one sample, all right, your sample mean may not be equal to the population mean. But if you do a sampling distribution of means, then you get closer and closer and closer to the actual uh, mean of the true population. That brings us to what we call the central limit theorem. Now, the central limit theorem tells us the sampling distribution of means, okay? And it tells us three things. It tells us that this distribution forms an approximately normal distribution. And we would expect that because if our population is distributed normally, most of our samples, at least if they're large enough, will also be distributed normally. And if you take a sampling distribution of the means, then you would expect a completely normal distribution. The sampling distribution of means has a population mean equal to the mean of the underlying raw score population. All right, in other words, mu is mu. All right, and the more samples you take, the closer x bar becomes to mu. And finally, the sampling distribution of means has a standard deviation that is mathematically related to the standard deviation of the raw score of the population. So again, S or the value of the standard deviation for the population is equal to S sub x. Okay, and again, the more samples you take, the closer you get those two numbers to one another. All right. These three things are what we refer to as the central limit theorem. Now, if any of you took calculus in high school or even pre-calculus, you may have talked about limits in your math class. And essentially, that's what this comes from. The closer you get to a certain value, the more accurate that value becomes. Now, another issue that or another definition, I should say, that we come up with is that of the standard error of the mean. And what this is the standard deviation of the sampling distribution of means. Okay? So the standard deviation of the sampling distribution of means is called the standard error of the mean. And the formula for the true standard error of the mean is the one that you see on the bottom. Okay? This symbol here represents the true standard error of the mean. This is the standard deviation of the population. I'm sorry, of the sample, rather. I apologize. This is the standard error of, no, actually, it is the population. I was right the first time. And then the number down here is the square root of the number of items in your sample. All right. So the standard error is equal to the standard deviation of the population divided by the square root of n. Okay. So this is our formula here. Now, how does this all relate to the value of the z-score? Well, once you've got the standard error of the mean, you can use that to actually calculate the z-score based on the sample mean and the population mean. And it comes out looking like this. All right. You'll notice that we've got the z-score on the left side of the equal sign, and that is equal to x bar minus mu over the standard deviation, or the standard error, rather. And so x bar, of course, is the sample mean. Mu is the population mean. And the item on the bottom of the denominator here is the standard error. Okay. And so this is the formula for computing a z-score for a sample mean. Okay. This is the formula for calculating a z-score for a sample mean. Okay. Now, dun, dun, dun. All right. Now, once you've got the calculation here, and we can calculate a z-score, now we might want to talk about the relative frequency of the sample means. And just as with raw scores, we can transform all the sample means in a sampling distribution of means into z-scores. And this results in a roughly normal z distribution, all right? A normal curve with all of the standard deviations there, all right? So we can take our sample means in a sampling distribution of means and convert them into z-scores. All right, so we're using the same idea that we did in the formula on the previous page. Okay. All right. So at this point, it's time to put our knowledge into practice here. And so what I'm going to do is we're going to start with the same data set that we have been using all along. All right, we've got 18 data points here. So the value of n, of course, is going to be 18. And here it is. Do you remember this and what it looks like? Well, where am I? Here I am. Okay. So I know that my value of n, excuse me, is equal to 18. And if, come on, please. If you recall, the value, if this represents a sample, or if it represents the entire population, that mean value, if you remember from way back when, was 13.67. All right. If you add up 14 and 14 and 13 and all the way to 15, You add all 18 of those values up and you divide it by 18, you get 13.67. All right, so that's the mean value here. The standard deviation of, if we call it a sample, is Sx. If we're dealing with the population, it's rho x. And this, if you recall, again, we calculated this a few chapters ago, is 1.56. All right. And so with that information, we want to know how to calculate the z-score. Well, go back to the formula that we talked about a couple of slides ago, and we've got z equals x minus mu over the standard deviation. And so if you know that the value of mu is 13.67 and the value of the standard deviation is 1.56, then if we use this, come on, and we're trying to find a z-score for a raw score of 13, well then, x is 13, mu is 13.67, and the standard deviation is 1.56. Well, 13 minus 13.67 is negative 0.67. Divide that by 1.56, and you get a z-score of 0.43. Now, what that means is that 13, if we have a normal distribution, and here's the mean, all right, standard deviation 1, standard deviation 2, standard deviation 3, this point, here's our x-axis, this point is going to fall somewhere right about there, right? Because this is the mean, which is 0. This is negative 1. And so this point is going to be about half of a standard deviation below the mean value. And so that leaves us with a z-score of negative 0.43. Okay. Now, same set of data here. And I'm not going to bother trying to write out the all of the values again. Just remember that mu is 13.67 and rho is 1.56. And in this case, I want to know what the raw score is for a z-score of negative 2. Excuse me. So again, here's your normal curve. Here's the mean, 1 standard deviation, 2 standard deviations, and 3 standard deviations. So negative 2 is this value right here. But I want to know what the raw score is. All right, well, it's going to be 2 standard deviations below the mean. Okay, so I know that the mean is 13.67. I know the standard deviation is 1.56. And so I want to calculate the value of the of x.
It's 5 o'clock.
Well, thank you, Jesus. The raw score. So rearranging the equation that we saw in the previous, or a couple of slides ago, x, the raw score, is going to equal z times the standard deviation plus mu. So negative 2 times 1.56 is 3.12, or negative 3.12, and add that to 13.67, and you get 10.55. All right. So if you know that your z-score is negative 2, then the raw score in this data set that is associated with that z-score is 10.55. Okay. All right. So good so far, I hope. All right. Let's do another example. Let me move my ugly mug out of the way here. So if the mean of a sample is 13 and the value of n is 18, the population mean is 12, and the standard error is 2.5, what is the z-score for this sample mean? Well, this is actually a two-step process, all right? Because in order to figure out the z-score, we need to have the value of the standard deviation. using the formula for the standard error, which we know is the standard deviation divided by the square root of n, we can then calculate the standard error as, in this case, 2.5. Actually, I don't know that they've done this correctly. I think what they meant was that this should just be x, not x bar. It has to be, because they've plugged it in for consarn it. They've plugged it in for x instead of x bar. So the standard error is 2.5 divided by the square root of 18. The square root of 18 is a little over 4. So 2.5 divided by a number a little over 4 is going to be a little over a half. And so 0.589 works out to be a reasonable answer here. Okay. So now I know my standard error. With that information, I can then go to my next slide and show you how to calculate the actual z-score for a sample mean of 13. All right, the z-score is going to equal the mean, the sample mean, minus mu all over the standard error. So 13 minus 12 all over 0.589. 13 minus 12 is 1 divided by a half is a little over a half, is going to be a little less than 2. And so 1.70 seems to be a reasonable answer for this. Okay. Now, my suggestion for you before we end this video is to get a plain sheet of white paper and start to make a list of all of the formulas that you know. All right. If you have all the formulas in one place, it will be easier for you to start doing homework assignments and quizzes and things like that. So write them down all on one sheet of paper and use that as your cheat sheet for homeworks and quizzes and whatnot. All right. So that is the end of the third video for chapter 6, and I hope you learned something.